And it's very fun to do this. I've actually done it and it's really fun. You should do it. Because the first thing you'll notice is you'll start walking like a robot. I'm incredibly proud of like how capable Neo is. I'll start there. Like the robot is just 30 kilograms, but it can squat or deadlift 70. And like it can use its entire body for manipulation. It can do everything from walking and running to crawling. It's fully dexterous hands, all these things. But what I'm the most proud of is that it's not an industrial machine. It's kind of like more like a Baymax. And it's no pinch points. It's soft on the outside. It's very low energy. It's very lightweight, and it's inherently safe. And that's been one of the major design constraints in the system. It has to be safe. Where you plot the increase in torque density of motors versus the increase in compute power, basically torque per watt and compute per watt. And then you see compute per watt is kind of like following exponential. And then torque per watt has been completely flat. There's been like no innovation in that space. And that huge gap has really hampered robotics. So I think one of the biggest mindset changes that we kind of did when we started was like, that is the real problem. Like the compute problem is solved, but it's not just about the compute. If you want to have the correct dynamics of how your system should interact with the world and move, then it's actually a power density problem.
Your actuators, I understand, are absolutely amazing. Someday I'd like to find a little bit more on how you're doing that, but to be able to get that power density is something else. And definitely, yeah, 1X is a company to watch and to watch closely. Okay, so what I'll ask it as kind of like a giant question, and then I can re-ask the different parts. But you probably get asked this all the time. I get asked this all the time. I have my own answers to these questions, but I would like to hear your answers because I have a feeling they're similar, but yours is going to be a bit nuanced. So the very first question you were probably asked is like, why the humanoid factor? I mean, why do we need to make a robot like that? And so let's just imagine that you've decided to do that and you've assembled an engineering team and you're in a room together. And the first argument that breaks out is like someone says, why do we need that factor? And you've got to settle that argument. And eventually you settle the argument that everyone agrees, or the engineers who don't leave the room. Okay, it's going to come down to that. So that's the first question you're getting asked. Then when you get into it, everyone's going to start saying, okay, how important is mobility? Do we need legs or do we do it with wheels? And then the argument that goes on there, you've got to settle that argument. Then eventually you get to the hands. Everyone says, well, how many fingers does it need? And then you try to figure that out. And then when you finally decide you're going to have hands, how many digits are going to be on the hands, then the argument is like, well, what sensor suite? Do we need any on the hands? What needs to be there? And then when it comes to the cameras, well, where's the placement of the cameras? How many cameras are we going to have on this thing? You keep on going down that list with all these different things. I'm sure you had those debates internally, what was going on, right down to what is like the battery life of this going to be? What's what size battery? Should it be a swappable battery or not a swappable battery? And every humanoid bot company has had that same set of arguments and debates internally, trying to settle it. Many of them have come to say similar conclusions. Some of them have come to different, but they're coming there because they're trying to solve the problem a different way. And that's why I would like to know why you settled on the first designs that you had. And now when you're going from Eve to Neo, you've made some changes, but again, you had to answer those. So if you want, we can start at the top and then we can go down that list and go, because I would like to know the nuance, because sometimes I have a hard time answering that question too, when the first thing is, why humanoid bots?
Sure. So I think I'll start from a very high level and just say what we are trying to do here is to clone the human thought process and also the action process of how we do work. And all of our knowledge is encoded in human form factor. So if you think about reusing most of the information that's available in large models already or in internet scale data, it's all encoded in human form. So like if you ask GPT-4 how to open a jar of jam, they'll tell you to hold it with one hand and like uncork it with the other one. So that's the embodiment of the world model that is kind of seemingly a bit represented in these large models, right? I want to get back to later how we train very large world models that contain a physical embodiment, but it is very similar. And this knowledge is encoded in human form factor. And now, of course, if you want to transfer also knowledge through expert demonstrations, so what we do for our humanoids is that we have our fleet of operators who then actually embody the robots through a VR teleop system and sometimes combined with vocab, depending on the complexity of the task. And then you're actually doing work remotely. So not only are you teaching a robot how to do something with its body, you're also actually doing the labor. And this is a very efficient way of solving the catch-22 of how do you get enough data for your robots to be useful, because you need to do useful work from day one. And the closer you can get your robot to the actual both dynamics and kinematics of a human, the better this transfer of knowledge becomes. So this kind of brings you back to the sensor suite, right? So the simple answer is you want the same sensors as a human, because the human is teaching the droid how to do things. And the optimal way to do it with the droid should be the same way as the optimal way to do it as a human, because the systems are so similar. That just sidesteps one of the biggest problems in robotics, which basically is the cross-embodiment problem. And this also goes for tactile and everything else. So I think the interesting question there is more, what order do you do it in? And how much complexity do you need to handle in generation 1, 2, 3, 4? If we say like we're on the verge of like launching iPhone 1, and then we're talking together in 15 years and we have like Neo 15, and what order did we do things in? That I think is a deeper question. But when it comes to also, of course, the spaces around us, all the infrastructure and the homes, they're human-centric. They're made for us. But I think equally interesting and very important to me is I would really like to live in a future where our spaces are made for our quality of life and comfort of living, not for the efficiency of machines. Like, why does everything need to be flat, etc., right? It is mainly because we are accommodating the need of machines, not the machines accommodating the needs of us. I think it would be really awesome if we could flip that around. Now, talking a bit more about the cost and the scale of it, what we're really trying to do here is to build the PC of the physical AI revolution. And there is nothing more general than the human form factor. So up through hundreds of millions of years of evolution, we kind of emerged as the best manipulator. And I have this completely unproven theory, but I believe in it. That like if you reset evolution and try it again, like humans would still win in the end. And it is because of our ability to manipulate. There's no other known species that can exert as large forces or such a large workspace on such a small envelope as humans. So I think the question of like why humanoids and do you need to be a full humanoid really comes down to, do you think this is a narrow wedge approach where you tackle one small market first and then you expand? Or do you think you should go for make the completely general system so that you can gather as general of a data set as possible and solve something closer akin to artificial general intelligence, where your system knows how to complete long-term, long-horizon planning tasks, knows how to recover from failure, and exhibits these kinds of common sense that makes us very efficient in everyday life. And this goes across all kinds of modalities. everything from communicating with language, communicating with body language, communicating with gaze, knowing who talks to you, when to interrupt, when not to interrupt, and doing all kinds of physical labor, all the way from simple tabletop manipulation to being able to bend down, sit on one knee while you're leaning with your elbow on the living room table, to stretch under the couch and get that toy that got stuck under there and pull it out. All of these things are kind of encompassed in the humanoid form factor. And that's really where we have conviction that this is a problem that is so complicated that if you want to solve it in a cost-efficient manner, you need to solve it at scale. And if you want to solve it at scale, then the human form factor is the most general of them all, as far as we know.
Yeah. Now, I'll give your theory a thumbs up, which I think we all know from the standpoint of evolution. That's why we're such good manipulators. It's the opposable thumb. That was the magic trick.
So I think if you think about it from the evolutionary standpoint, it is interesting to try to remove things. I know this is a question you're found of, right? And in the beginning, the reason we started with wheels is actually very simple. So what is useful is manipulation. Locomotion in itself is not that useful. Yes, you need to go somewhere to do something, but that's not really the hard problem. And in the beginning, we didn't have the power efficiency to make a system that has these soft, compliant, adaptable properties that we really want in our robots to be safe and to be able to learn efficiently. We weren't able to do that in a power efficient enough manner to go on missions for hours while walking. So we said, okay, let's start top down, because the most important thing is that we can do useful work, and we do useful work with our arms, our hands. And we need the envelope. So we need to be able to bend down, sit on our knee, all of these things, lean in to push, lean back to pull. So Eve actually is a fully balancing humanoid, even though it has wheels. You can think of it more like a Segway type of rope, like a human standing on a balance board. And the reason we are now going to legs is not actually so we can walk on stairs. And I feel the field is kind of obsessed currently with walking. And as someone who's been in the field for a while, I would argue that walking isn't actually hard, because walking is just manipulating the ground pretty crudely. What is hard with walking, of course, is the power efficiency to make a system that can do this over time, not run out of battery, not fail due to the impacts that is happening when you're stepping, all these things. But from an AI perspective, it's not that hard. Now, the reason we go to walking is not because we want to do stairs. There's enough of a market with flat floors, or even if we think about the domestic use case, there's enough holes on one single floor. The reason we go to legs is that legs makes us better manipulators. So we really want to ensure that we are able to use our legs to reconfigure our support region, right? So put your legs a bit apart to be able to push really hard, or very close together to shuffle in between the couch and living room table, and really operate in these tiny spaces that we humans operate in every day without thinking about it. And also using our entire body as a manipulator. And most of the manipulation that happens is not really only with your hands, especially in the domestic case. So I've been living with one of these at home for a while now. And one of the things that surprised me the most when observing this is almost any task in a home requires you to use multiple points of your body to do the manipulation task. Like you're leaning your knees on the cupboard to reach in over the counter and get that glass in the top counter, or you're bracing yourself on the cupboard to open the refrigerator that's stuck in vacuum, or like I mentioned earlier, right? You sit down on one knee and you lean to look up at the couch. All of these things require you to use a lot of your body in contact with the environment. And that's really what's unique about our biped Neo that's coming out soon. That it's not that it's made for walking, but that it's made for using its entire body to do useful labor. And walking is a byproduct of that.
And I think that's an important point, is to to realize that the legs are more than just about manipulation. It's about a lot of other things, the reconfiguration of it. And I think I would agree that walking is not a hard problem. The people at Honda would have probably told you, man, it took us 30 years to solve. But then if you look around there, it's like, if it's such a hard problem, how come so many people seem to be solving it all at once, all over the place, these different companies? So I agree. While it's a difficult problem, it's clearly not an impossible problem. It's kind of a solved problem. I argued that once the Segway came out, it was basically solved because it always was a balance problem. But the problem has really been from the hip up, because if we go back to evolution, our brains and our hands co-evolved for a reason. And that is because we needed the brain power to manipulate the hands, and then we needed the dexterous hands to go with the brains that we had. So if you kind of look at that, it's like, wait a minute, this and that's important. Don't worry about what's down there. That was solved hundreds and hundreds of millions of years ago by evolution. And we can definitely strap that on when it's needed. But your insight there is very interesting because, again, this is why I wanted your nuance. You're answering that question of why legs very differently than anyone else has answered that. It's, and again, that you could argue the wheels have so many advantages. And again, a lot of apartments are literally called flats for a reason. They're flat. They don't have a second floor. So you can operate in that space. So that's very interesting. And then I guess, if we're going to move on, we talked about the fact that you have the humanoid form factor. There are going to be some people saying, well, why not dogs? Why not spiders? Or, why won't those be better for other things?
Two things on that. First of all, why not dogs or spiders? Because I don't think my family would be happy with Rosie the spider home assistant. I think there's some human-machine interaction challenges there. But I think it is very interesting to say almost all technology follows two cycles. One is, if they're very disruptive, they actually start in consumer and then tickle up into industry. It's very hard to find examples of the opposite because you need to really have a lot of supporters, early adopters. You want to ride the consumer adoption wave, all of these things. And you want to have people who is less risk averse. The other one is all these kind of technologies goes through a cycle where first you have very specialized systems because these are very hard problems, right? Kudos to Honda, like I said, because Asimov was an amazing project. And I grew up watching that, right? It inspired me to do what I do. And they were so ahead of their time. But there's some lessons learned there also. Because 25 years ago soon, Honda Asimov was running across the stage and walking up and down stairs, handing someone a ball. But it didn't actually leave the lab. And I think the simple answers to why are really three things. It's the AI wasn't ready. Everyone agrees on that. But then there's two more. One is the system was nowhere near cost efficient or manufacturable or durable. So the entire, and they pushed this for 30 years. So they pushed that direction of robotics to the limit. This is basically, I would argue, this is as good as you get the classical industrial approach to robotics in a humanoid form factor. And so that's a scary pitfall, right? If you do the same thing, you'll end up in the same. You might do it in 5 or 10 years now instead of 30, but you'll reach the same wall. And then the other one is that it's not safe, because even though Asimov was pretty light for what it was still pretty heavy, very hard, a lot of energy in the motions due to the gears. So it's not just about the AI, but it was an incredibly impressive system. Now, sorry for the tangent, but I get back to the other reason here. Then it goes through two cycles. You start with specialization because the problem is so hard. And in robotics, you've seen this with industrial automation in car factories, for example, and robot arms. In the PC and compute, you saw this with very specialized computers for universities and then for financial, etc., and engineering. And then came the PC, because now you're creating this enormous market because it's so generable that you get an explosion of applications. And this is what is happening now, right? Because we're taking these digital innovations and turning them physical. And if we build the right foundational hardware that can actually do anything cost efficiently and reliably, you get to scale. And now you have this explosion of applications. Once this has happened, the market is so large, right? When we have billions of robots around the globe doing most of our physical labor, there is going to be specialization again. Because now the market is so big that you're actually going to start building specialized droids for specialized tasks because there's so many droids. So now this makes sense again. And this is, for example, now happening in compute, right? Now you're seeing specialized compute solutions again because the compute demand with AI is so big. I feel like this is true for most kind of like societal changing products that operate at this scale, that they go through these cycles. And I do think the same will happen with robots. So in the end, we will end up in like a Star Wars-like world, right, where we have all kinds of droids for all kinds of tasks. We need to go through the general form factor first.
And even then, they'll probably be, they'll still be kind of humanoid, but different types of humanoids. Because even in Star Wars, there were a lot of humanoids, but some were not as sophisticated as C-3PO. And then, of course, you had the others like R2-D2, which are completely different. You know, my argument is that you will have a few. You'll probably have the robotic dog because they're much better at getting the slippers from underneath the bed than the humanoid form factor. And maybe have spiders to literally crawl through the walls to find things that you can't other. So you would see those, but you're right. You kind of start out there. And the other unfortunate thing that Honda went through is they didn't have the advantage of the convergence of these technologies. So they were really working with very archaic stuff. And when you look at the first Asimov bot or the first walking bot they had and the computing system they had on top of it, like this was literally like this huge table on top of this legs that was trying to walk up the stairs with the PC on there and a big screen display. Because remember, they didn't even have flat screen displays yet. It's like all this stuff when you begin to look, it's like really impressive that they could make something with that ancient technology, be able to carry a payload like that up the stairs. So that was like one of the things that really held them back. And you're right. They kind of, it was like that thing of the miners going through there. And when they're like 6 inches away from the gold mine giving up, it's like they stop in 2017. It's like, oh, the technology is finally there. Take your team and repivot.
It's interesting what you say about the compute though, because I have this very interesting plot. This was actually originally given to me by Jared Pratt many, many years ago. He's the CTO of Figure now. But increase in compute power, basically torque per watt and compute per watt. And then you see compute per watt is kind of like following exponential. And then torque per watt has been completely flat. There's been like no innovation in that space. And that huge gap has really hampered robotics. So I think one of the biggest mindset changes that we kind of did when we started was like, that is the real problem. Like the compute problem is solved, but it's not just about the compute. If you want to have the correct dynamics of how your system should interact with the world and move, then it's actually a power density problem. And then like muscle is amazing at this, right? So like I said, pretty proud to say like the motors we have in-house now, and this is like the definition of vertically integrated, right? We make the machines that make the copper dies to form the coppers into how we assemble motors. Like all of this is done on our line. They're about 5 times the world record in torque to weight. And you can do this interesting experiment where like if you pretend that you take your round motor and you just cut it. So now you unroll it. And then you look at the shear force. Then you can compare it to human muscle. And you can say like, okay, roughly how much force per weight, roughly how much force per volume do we get? And we get like 75% force per volume and 80% force per weight. So we're still actually not there. We still like have a gap to close before we get to human muscle. But it's a lot more than like anything else you can buy off the shelf at least. But still, there's still a gap. And the gap used to be very big, right? When we started with this, the gap was like a 5x. Like you needed 5 times as much motor to get the same as you have with human muscle. In our robotic space, just like for the automotive space, when it comes to electric cars, most of the innovation and what really built the competitive advantages were on the battery and like the power electronics, the battery and the drivetrain. For humanoids, it's going to be motors and actuators. And like, how do you get rid of the classical high ratio harmonic drive typically kind of industrial robots that are stiff, high energy, dangerous, and move towards dynamical systems in a manner that you can miniaturize and pack into a humanoid that is small enough that you would like to have it at home. And there's still an enormous amount of work to do there, and can't talk too much about it yet. But like, I mean, there's a Neo 2 already, even, right, that we're thinking about as we're commercializing Neo 1 now. And this is a field that's going to progress very, very fast because very little, well, hundreds of thousands of people, literally, right, were working on increasing compute per watt. Almost no one on the planet was working on how do you increase torque per watt.
And do you have your own sort of, I mean, what do you talk about? I've never really heard that before, but it seems like you should come up with that scale or that factor. You know, just like you got Moore's law, maybe there needs to be like Bernt's law or something like that, on exactly how you define that and put it out there. Because I think that's a very interesting metric that everyone should start tracking, to really look at it as relation to human muscle and kind of power they have there. There's another question I like to ask is that you've used kind of a favorite term of mine many times that we've heard also other people in the humanoid bot space use. I would like you to define before you hear my definition. That is, what is your definition of useful work?
Oh, that's a good one. I have a very, very simple definition. If you want something done and I go there and do it, let's say you say, can you tidy my house? I say, okay, sure, I'll do that. So I start doing that and I time myself. It took me 30 minutes to tidy your house. Then that is what I call 30 minutes of human equivalent labor. And now our metric is how much does it cost me to serve you 30 minutes of human equivalent labor? And this happens through a combination of AI and operators using teleoperation. So the cost metric to driver is pretty simple. Like, what's that efficiency? How many dollars do I need to put in to get half an hour of human equivalent labor? And that's probably the metric we're going to push for the next, I don't know, at least 3 years.
Okay, I think that's kind of close to what my metric is that, I mean, the first is it has to be able to do the same task as a human, hopefully with the same reliability in about the same time scale. And it has to do it at a cost that would be competitive to the equivalent wage for doing that. That I go just a little bit further is that you want to be able to do it with a certain amount of duration and reliability, that, you know, that it can do it for an entire shift and also come back for the next shift without requiring like lots of maintenance and everything else. So I think we're pretty close on that. But, you know, I'm looking at it from the standpoint that if you're going to deploy the bots into an environment, in a manufacturing environment, it has to somehow be cost competitive. So that's basically what an accountant would look at. He's going to look at all these.
I think cost competitiveness is one. And here you get into something interesting, which is why I think like manufacturing is not necessarily the best first market, because you're turning yourself into someone with the same problem as autonomous cars. Now, if I'm on a car assembly production line, the amount of mistakes I can make is infinitely small, right? You got to keep the line running. Humans are very, very good at this. And if we make a tiny mistake, we recover it in like 3 seconds. Oh, that bolt didn't pop in fully. Let's do it again. Okay, there we got it. And I'm like, I'll catch up those 2 seconds that I lost on cycle time on the next one. We're getting there, but we're not getting there without very, very large data sets of embodied actions in a very diverse setting to get you to common sense and how to recover from these kind of partial failures. And if you think about the whole, I want to talk a bit about the whole, because for Neo, the main market we're launching towards is domestic and the home. And if our robot is tidying your house, doing your laundry, cleaning the house while you're at work, if it did it 85, 90% correct, you're probably very happy. That's not true in manufacturing. Now, also, if you would have used 1 hour, 1.5 hours to do this, and the robot used 4, you don't actually care. You're still very happy. So, and lastly, by doing this, and by also being kind of an entertainment device and something that you can also teach yourself to do things you want the robot to do during the afternoon, and something to play with and have fun and bring your friends over, we have this enormous transfer of knowledge into the machine that you would never have in your cage on the manufacturing line, whether you're just standing there putting one panel up underneath the car every day. That type of labor is extremely useful. But I think the path to get there, to where you can do these kind of labor efficiently, is very hard. You almost have to get close to something we could start talking about as an AGI before you can solve those tasks to the degree that you would like to do so from a reliability point of view. So for us, the path is really start with doing as many diverse tasks as possible in as diverse a setting as possible. Get to common sense where the robot really understands, how do you recover from partial failure? How does a task actually work? How do I ask for help? How do I interact and work together with people to complete tasks? All of these things. And then you go to these other markets. And we're already, we have a lot of droids at this point. We're coming up on soon manufacturing our 100th droid. And we have about 50 of them in daily operation doing a very wide amount of tasks. And what we're seeing here is the same as we saw earlier for large language models, that if you want to get generalization, common sense, and some kind of spark of intelligence in there, it comes from the diversity of the data, the width of your distribution. So you want to do as many different tasks as possible, as complex as possible, in as different environments as possible. And that actually scales a lot better than just your amount of data. So we like to say there's these 3 things to care about. It's the diversity of your data, and that's the first one and the most important one. That's the quality of your data. So who collected your data? How correctly is it labeled? How good did they do the task? The quality of your data really matters. And then it's the amount of data, because in the end you need scale, because these models aren't small. So they need a lot of data. But that's really the order of operation. And I think that is the path to solving these problems.
And what is your preference, simulation versus reality?
What we do is what we call complete end-to-end learning. And what I mean by that is that into our neural network goes basically the state. So that's what the robot can see, what the robot saw a while ago, the state of the system. So what's the position of the arms, the joints, the velocities, all these things, any kind of proprioception, tactile, in general sensors. And then the desired action that we want to complete, and out comes the action the robot actually does. So there's no neural network that says okay, let's segment the world into that's a car, that's a table, that's a dog. There's no SLAM where we say, okay, let's 3D reconstruct the world and figure out where we are. There's no grasp library figuring out grasp points. There's no manipulation library computing trajectories. Everything is one big transformer, data in, actions out. And if you want to train this kind of a network efficiently, then first thing I would like to say is, in simulation, to learn something, we usually need a few million samples. Then we can do a good job on some task. That's pretty trivial to generate, because you can just run faster than real-time simulation, and in a few hours you can probably get few million samples. Now, what we don't talk enough about is now we're going to train a very large model. So if I do this in real instead of in simulation, 10 to 50 samples, and I can automate a task really well. So like if you have a complex manipulation task that you want to learn, you can usually learn it in like 10 to 50 samples at the current scale of our networks. So of course you have a very large foundation model that you add this into that we've already trained, but that's now if I wanted 1 million samples instead of 50, the amount of compute I would need to spend would be pretty immense. And in the end, everyone runs out of compute and everyone runs out of data. Now, you can kind of band-aid this by saying, oh, I'm going to run simulations. So now you're not running out of data anymore, but you are running out of compute. If you can be very, very frugal about the diversity of your data, the quality of your data, then of course, you still need some scale. But your sample efficiency is many orders of magnitude better. So now you can actually train very, very large role models with a relatively limited compute budget. And with a very large compute budget, you can train extremely good role models and start to approach these common sense and generalization concepts in a very good manner. I think it's super exciting to see that we're actually starting to see some of this now. So if you look at some of our videos, you might see some what we call like recovery behaviors, which is now consistently across like all the tasks we're doing, where we see the robot is very good at understanding that it's failing, even at a complex task, and then correcting itself and finishing the task. And also we're also seeing some versions of what I would call like true zero shot behavior, which as far as I know is a first in robotics, where the robot is able to do tasks it never trained on. Success rates of this is still pretty low, but it does succeed. So it can like get a task to do something it's never trained on how to do it, and it actually succeeds on doing it. And this is what you will need if you're going to solve the general problem. And I think it's then incredibly important to think about your sample efficiency, and that means simulation is very hard to pull off. Now, the other side of it is that why do you have bad sample efficiency in simulators? And this is, of course, because a simulator is nowhere near to reality. How deep do you want to go? You can go all the way down to like the quantum level of how things interact, right? A simulator is very crude with respect to simulating contact interactions. The other problem with a simulator is that it doesn't actually have good agent behavior. So if you want to learn how to behave around people, then you need to simulate the people. So now you kind of like have a psychic problem here. How do you get the data to simulate the people? So what we do instead is actually to get some more leverage from all our data, we do train in simulation, but we train in simulation that is made on our data. So we take all of our data and we use that to create a large role model that, given the state and action we want to take and a current observation, it can predict the future. So you can think about this like a model that can see from the robot's eyes and say like, okay, I'm standing here, I can see a door, I get a task of like being in the room on the other side of the door. So now I know that to do that, I have to go through the door. So I have to go up to the door and open it. So 2 seconds from now, how will the world look? And then you will see like, okay, then you get a video of the robot approaching the door, starting to open the door, because it's predicting forward in time. It's kind of like Sora from OpenAI, except it is grounded in reality because it has a physical embodiment. And you can actually run learning in these models in the long term. And I think currently a combination of learning and search in these very large role models, that is our best bet on how to approach AGI. And also most likely, like when, for example, OpenAI talks about Q-star, for example, that is very similar, right? That is just one search algorithm. But what it's really about is not the search. There's many ways to implement that, and there's also like different types of reinforcement learning you could do to more efficiently to search. What it's really about is, can you actually build a very, very large, consistent role model that captures all of the dynamics of the world we live in, and also all of the agent behaviors and thought processes of all the agents in this world. And if you have that, you can just say, I want this to be the end state. I want this to be my goal. And you can search backward from your goal. Well, how did I get here? And that's a very efficient way of solving the general planning in a completely end-to-end learn manner. And I think if you want to pull this off, we're talking so large foundation models that you have to care deeply about your sample efficiency. And then simulation is not as efficient.
I think, when you're not even thinking about the different agents you're talking about having to deal with in an environment, it's really easy to simulate a robot picking up a box. You kind of get it close, but it's close. But when we want to go into folding a t-shirt, that's really hard to do in simulation. So assuming you can even model that, the amount of compute you would need just to model that correctly is like an order of magnitude more than just getting the box right. And I agree. With the box, it's all about the contact. And the funny thing about, most of the physics engines that you have out there, everyone thinks that what the physics engine is doing is solving F equals ma. That's way, way, way down at the bottom. What it's solving is the contact problem, because you can't apply the forces until you know where the contacts are. So it's really a collision detection problem where they're trying to figure out where it is with a flawed model of what the objects are like. They're assuming everything is flat surfaces and everything else. So you approximate where the contacts are, but we know the real world is really messy. So when my hand grabs this thing, the contact points are that there's so many of them. I don't know how you simulate that correctly in simulation. And that's just so it's supposed to be a stiff bottle. We start dealing with a t-shirt. Yeah.
One thing is the contact points, right? But like, even if you think about simulators, almost all simulators have some kind of contact model that is spring-based. So like you just say like everything interacts as it's roughly the spring dynamics, which is not true at all. Actually, we do a lot of hardcore work in mechanical engineering, right? So I have a simple analogy for this. If you want to solve something as simple as how does this bolt interact with a certain torque, bolting two surfaces together, how does this interact under a certain load? Then you like run a simulation for a day on a small compute cluster. And then that's still not quite accurate.
Yeah, that's a hard problem.
So that real-time simulation you do in a physics engine is like, it's not even remotely accurate. There's still data in there. You can still learn from it. I'm not claiming you can't learn. And for some things, it's actually very useful. So if you think about how to bootstrap, for example, walking. So you need to mix this with the rest of your AI, right? Because like I said, walking is, your feet aren't just for walking, they're for manipulation. But if you want to just get a good way of like walking as one of the behaviors into your model here, that can actually be learned pretty well in simulation. Because your feet hitting the ground it's not that detailed, right? It's not like finger precision and dexterity. It's just like a flat thing roughly hitting the ground with the right force, and then you won't fall over. So that actually works in simulation, but the manipulation problem is extremely hard to do in simulation.
Yeah, what seem like simple problems are actually very difficult to properly model in physics. So all of engineering is an approximation just so we can get an answer really quickly. And in the end, you have to go in the lab and actually test the stuff out to verify that your model is even reasonably accurate and guesstimating what the answer is going to be. So yeah, I could see that be very messy. So now, which is more costly, to scale up your compute or to scale up the number of bots that you have?
That's a great question. Scale up compute is the answer for us, but that's because of some choices we made, right? So since we're starting to get pretty public now about like one of the big target markets for Neo is consumer and domestic. That means we need to have a pretty disruptively low cost compared to anyone else. And most systems these days are in the hundreds of thousands of dollars, right? Because humanoids are complicated systems. You can't scale that to that extent. So really what we've done here is take like a first principles approach. We started 9 years ago with this. Like how do you design humanoid that is very, very scalable in manufacture? And then build the entire line and like build the machine that builds the machine, right? To be able to do this really well. And we're now at a point where we can reach these cost targets that we have set. And this means it's actually more cost efficient for us to deploy a large fleet of robots and then be very sample efficient than to just blindly scale compute. And now, of course, this is also very useful because in the end, you need to have a lot of droids out there if you're going to learn the real problems, because we don't know how this will pan out yet. In full transparency here, I mean, we do a full few trials, but I'm super excited to really start rolling this out at scale and seeing how people use it. And there are so many non-robotics related questions here when it comes to the social interactions and how this is a part of your life. When it comes to privacy, especially, because without your data, we cannot provide you a good service, because we need to automate things in your home, and your home is unique. But I want us to really be big sister and not big brother here, right? And we want to make sure that you feel that you have agency over your data. You are in control, and that we treat privacy with the utmost respect. But all these things we kind of need to learn as we deploy and start to scale the system, and in collaboration with our early adopters and kind of almost like entrepreneurial customers, right? The first few customers to get this and really spend time with this and figure out how does this work, because I've been working with this for 9 years. So clearly at this point I am blunted. So when I have one at home, that's not the same as if you have one at home. And that's a lesson learned we had when also deploy our Eve robots, because we've deployed quite a few of them now into real applications. And no matter how much we tested in the lab, oh man, did we learn a lot when we actually did those pilots with customers. And then now we've done the pilots with customers. Now we know how to do it. And then comes the day when you leave your product with the customer. It's no longer a pilot, and you go home and the product stays. And then you learn a heck of a lot more that you weren't able to actually figure out while you were doing the pilots. And we're going to go through the same in consumer, right? And then that's going to be a journey. So looking forward to that one. I think it's going to be a lot of fun. And then I somewhat look forward to the manufacturing, which is probably going to be very painful. I think we've done a great job in setting ourselves up for being able to do so. But I mean, that's also going to turn into reality, and reality is never exactly how you expected it to be. So it's also going to be an exciting journey. I think those are the two big things for us coming up now in the near future. And then, of course, scaling the AI and see how as we aggregate more and more data, how far can we push this, right? And right now, the scaling laws look incredibly good, right? They're looking better than what I would say like they did in the early days of large language models. We think about like sample efficiency and compute efficiency for actually transferring skill and like getting to some kind of common sense. But who knows? That there might be problems, like suddenly you meet a wall. Doesn't look like it right now, but yeah, it's going to be exciting. Going to be some exciting years, that's for sure.
Now, I'm just curious about Neo. First of all, it's very interesting to see Neo in the background. I don't know what's standing there. It's just, I see that in the background. Because you mentioned soft robotic, and actually, I received a couple of questions from colleagues that we have to ask you about what is the soft element, because it's 30 kilogram.
But it can squat or deadlift 70. And like, it can use its entire body for manipulation. It can do everything from walking and running to crawling. It's fully dexterous hands, all these things. But what I'm the most proud of is that it's not an industrial machine. It's kind of like more like a Baymax. And it's no pinch points. It's soft on the outside. It's very low energy. It's very lightweight, and it's inherently safe. And that's been one of the major design constraints in the system. It has to be safe. And this is both because you want it to be safe for all people so it can work in our space, but also because you want it to be safe for itself. Because ultimately, in the end, what we will be doing is reinforcement learning in the real world. That is the end state, right? like everything else we're doing is to get there. So hopeful someday in the future, whenever your droid has nothing else to do, it'll be practicing on whatever it feels it's not so good at. And I really look forward to that day. And if you're going to do that, you need to be soft, because you're going to interact with the world all the time, and you're not going to be able to plan when you're going to make contact with the world. So it needs to be part of the passive dynamics of your system. Drive, which gives you kind of this adaptable, compliant joints, just like we are, right? So like humans are very adaptable and soft and compliant. And this is one of the things that makes us so great manipulators. So this is common misconception that we are so fast. We are not, right? Or we can move very fast, but we're not very fast in sensing. So like if I'm picking up this cup, I'm actually not really fast enough to sense that I'm touching the cup and stop my hand. What actually happens is that I see the cup, I know roughly how to interact with the cup, my muscles actually tense up to a certain impedance to brace for the contact that will happen, and then you collide with the cup. And then you collide with the cup with very well governed contact dynamics, because your brain is so good at like tuning your muscles for that specific contact. Now, our robots work exactly the same. We actually modulate the field in the motors to have the correct kind of tension and preload in the cables for these kind of contacts. And this enables you to do very safe, lightweight contacts. And this is passive in the dynamics of the system, which I think is incredibly important. So this is not something we can just control in software. When our system moves, there is just very little kinetic energy. Because normally in a robot, like if you think about like the joint moving with like a human speed, and you have a gear inside here, typically it would be like about 100 to 1 ratio. So something inside here rotates 100 times faster than my arm. Now you can think about something rotating 100 times faster than this, and then I can say like, oh, can you stick your hand in and touch it? You don't want to do that. That inertia, that energy that's in that spinning system is enormous. And you can actually usually compute this, which is an interesting exercise to do. So if you look at some of the typical robotic systems like humanoids, and you compute what's the effective, what is the effective inertia, equivalent inertia at the hand to the energy in this system, it comes out at about 15 kilograms. So you can, and about 25 for your feet. So you can think about strapping a 15 kilogram kettlebell to each hand and a 25 kilogram kettlebell to each foot, and you can go about your daily activities living. And it's very fun to do this. I've actually done it, and it's really fun. You should do it. Because the first thing you'll notice is you'll start walking like a robot. Because this is now your dynamics. Because you need to slow down before you hit the ground. Because you have a 25 kilogram kettlebell on your foot. And then you need to actually always be in balance. Because if not, you can't slow down before you hit the ground. So you can't do dynamic walking anymore. It's very dangerous. And this is why industrial robots are dangerous. It is all in the gear ratio and how this creates these very large inertias, or basically very large amounts of kinetic energy in the system when moving. So when I say our system is soft, it's because we don't have these inertias. So that means that the system is soft on the joint level. So not just soft on like with respect to like our muscles being soft, but soft on the joint level, which we humans are also. And it's a very important part of how we manipulate, walk, move, do anything. The other part that's soft on Neo is the actual outer part. And it's not just a fabric. It's the actual outer part of the robot is soft. And it collapses in on the tendons underneath to take up any energy that happens in impacts. And the reason for this is that we want the system to be what we call passively safe, which means we want, even on moving at like peak speeds of the system, we want the system to be so that if we, at some time, at some scale, should have an accident and involuntarily interact with a human, we should be below the safety critical impact that is typically said. Like, you have this Higgs safety index, which talks about what is the amount of impact energy before there's likelihood of severe injury or death. And you want your system to be below this threshold. Because when you have hundreds of millions of robots out there among people, things will go wrong. And I think we have a large responsibility in trying to make our systems as safe as possible. Now, of course, we will do everything we can in software to make sure things go well. But in the end, if you have a large enough scale, things might go wrong. And then you should have done everything you can to make it safe. And this is kind of like how I want to tie it back to, like, we so purposefully do this that we also try to make sure we don't select markets that turns us into autonomous cars, which is the opposite of this, right? Where your system can never fail because the consequences are so large.
Did you ever see any of this company using soft element? This is for Scott, maybe. Did you see something a bit similar to incorporate the softness in that? Because for me, it's pretty interesting. Of course, reducing the passive in the system to reduce the computation power and all this thing is for free.
The closest are the cobots, which were an attempt to, I guess, sort of soften the industrial robots so that they could be more safely used around humans without causing injury. So the design elements that you had, like force feedback systems, and then the joints might be compliant. So I assume your joints, yes, they are compliant. Are they back drivable as well? Usually the cobots.
They're very, very back drivable. Like
yeah. And so that's the problem with a true industrial robot is, like, they're not back drivable. So not only do you have a lot of mass that's moving around, you do have a lot of rotational inertia that you have to stop. And then a lot of these software control systems that have to work just right to detect that they need to come to a stop. So something has to detect that they're contacting, like it might be human, like, well, wait a minute, that's out of spec. I was expecting to do the move with this much energy, and now suddenly I'm coming in, and then you've got to react really quickly and try to stop it in the energy for doing it. So they designed the cobot to be round and soft, but still, you can get bumped by these things, and they have pinch points. They try to get rid of the pinch points, but someone showed me that still, even though the elbows don't have a pinch point, you can put a Coke can in there and it'll still crush the Coke can. Or if someone plays with the teach-pendant settings and, like, turns off the torque force feedback because they need it to actually do the task, you can defeat it. So, like, they're kind of safe, but they're kind of not. Your approach is like, man, it's like everything else goes wrong, it's still safe because it's not heavy. You don't have anything rotating really quickly. Everything is soft. Compliance is built in the system, back driving. And even in some cases with industrial robots, the fatalities that have happened with many industrial robots was not the fact the person was struck by the bot, but by the fact the person was pinned by the bot and they could not get out of that state because the robot then suddenly stopped, but it wasn't back drivable. So they could not push the bot out of the way. So, I mean, it sounds like Neo can fall on top of you and you can just push it away. It's like, it's not a big deal. Whereas an industrial robot comes down on you, it literally is coming down on you like a ton of bricks.
Yeah, no, I think that's very well said. And I think it is different, right? Because there's been, and I think this summarizes also a bit like the direction of the field, because in the beginning, you had these large industrial robots, and they were a masterpiece of engineering, because at the time, you didn't have that much compute power. So you wanted to make sure that, like, when I move my elbow, I don't affect my shoulder or anything else in my system. I can locally control one joint at a time, and they don't affect each other. And if you have these very high gear ratios, that actually happens because your system is so stiff. So it's like, by design, a beautiful system. And then once you started to do more complicated automation tasks, you suddenly were like, oh, wait a minute, we need some softness in the system. And you can start adding force torque sensors. But now we have to move very slow, because if you move fast, you can't really mask those. Like, there's a lot of energy that you need to, like, dissipate from your system when you are in contact. So if you're moving fast, you're not going to have time to do so. So you see these robots typically move pretty slow. And if you take a cobot and you run it a bit faster, like a meter per second instead of half a meter per second, and you collide it into a force plate, you can find good videos of this on YouTube. Those contact forces are super dangerous because then it's not fast enough to actually solve. And then some smart people said, well, let's put some springs in there. Because if we put some springs in there, we can like mask this inertia by also having a spring. So you got like serious elastic mark. And then now you have a system which is safer. Like you can still bottom out your spring, but it's safer. But it's a bit hard to control. It's a bit noisy and like it's a bit wobbly. This wasn't so well received by the market, but sure. And then comes some new robot arms where they like take it all the way out and say, oh, that's fine, we're gonna add some dampers. And then you have the ones who have like now motors on their springs and dampers to adjust the spring and damper coefficients again. And you're doing all of these things to mask the inertia that you got because you put the gear in there to begin with. So you're kind of like stuck on like you're just like looking in one direction, right? And what we really did was take a step back and said, okay, well, what is the actual problem here? What is driving the complexity? Because you don't want to have force torque sensors. They're very expensive. They drift, and there's a lot of problems. You don't want to have these expensive gears with very special metal alloys, like bendable rings and everything. You don't want to have these very fast controllers to try to mask your inertia. And at least you don't want to have like springs and dampers and everything in their driving complexity. You want to try to get rid of all of these things. And I think nature has done a beautiful job of this. And it is baffling how much nature actually sacrifices for this compliance and adaptability. Like if you look at like human muscle, like ATP to movement, it's about 25% efficient. So like an engineer would say that like, oh, that's terrible, like 25% efficient drivetrain. But the simplicity of the system, because you don't have all these other problems, actually gets you back the energy. So there's this, my favorite way of looking at this is like a human can run further on a liter of olive oil than a Toyota Prius can do on a liter of gasoline. So the total system efficiency is incredibly good, but the local efficiency of muscle is quite bad. And so I think if we can get to that, we'll be very happy. Muscle is pretty amazing.
Yeah, I think what you're describing, the expression here is like they're trying to fix the problem by putting lipstick on a pig. It's like you keep on adding more and more complexity when you're right. You got to go back to the absolute root of the problem. And the other thing is, when they developed industrial robots, is that you wanted the actual mechanism to match your mathematical model. And so you made everything stiff and encoders and everything to make sure that when I read those joint values, I knew exactly where the end of the arm was. I didn't even have to look there. I knew where it was just by measuring the angles. And so you need to make the system all stiff to be able to do it. You start having the compliant robots, and now they become very sloppy, and suddenly you think it's here, but actually it's somewhere else. And then how do we as humans solve that? It's because we get this sensor suite that we have a rough idea when we close our eyes where my hand has to go to touch my nose, and I'll get pretty close, and sometimes I'll get spot on. But once I open my eyes, I'm guaranteed to hit it because I know how to do the course correction. And so once you start adding that thing in there, it doesn't matter how sloppy your system is, you can make up for it like that.
Well, that is true to a certain extent. I would actually say we are pretty stiff. Humans and our robots also, they're pretty accurate. Because, when you think about whether it's like us pulling tendons through the motor drives or whether it's muscle or whatever it is, your skeleton is still very stiff. And the human skeleton also is pretty stiff. So if you think about like the angles on your skeleton and where you are, like your proprioception is pretty good. It's usually within a millimeter, right? Which is for like normal cobots about what you get with a cobot. So the adaptability lies more on like the compliance of the joint than the compliance of the system. Although there are, of course, systems, we're talking about like soft robots there. There are soft robots which are more like an octopus or snake or whatever, where, of course, you don't have these stiff skeletons. But for the type of robots that like we make or like how humans work, the system, like the skeleton itself is pretty stiff, but the joints are very soft. And you get this beautiful combination of both. Yes, you get this beautiful combination of both. You get like super good accuracy, but you get the adaptability and softness.
And what will happen sometimes with the cobots is if you get a heavy payload on there, because the joints have so much compliance in there, they will not really quite know where they are, which is why you might have a camera system or something like that to be able to compensate. And again, my proprioception, it's okay, but I have to practice, right? When I wake up in the morning, I'm like, might hit my eye the first time. You go, oh, let's calibrate for the fact that I've got a little bit of muscle atrophy here. I'm not taking that into account into my internal model. Then you quickly get into it. But yeah, I mean, that's the difference between the old days. You had to do it because we just didn't have the good measurement system outside of the encoders on the joints. So we wanted to make sure that was really in there. And the better you can make that, the stiffer you can make it be, the better. But then the end effect is that you hit something and it's really hard to get out of that. And that's why no one wanted to make these things soft, is because the problem became the art, and you're right, it became compute and measurement. And then the other thing is like, oh, I can put a camera on it, but how do I interpret the image? I can see the image, but how do I convince the computer that to understand what it's looking at? And that's like another thing. So it's not just having a camera, it's also the AI behind it, understand the environment and all that. So it's an incredible convergence of technology that allows you to finally do this.
I think it really is. And I think it also is different domains and applications, right? Because if you have a calibrated factory line, I would not use a humanoid. I would use an industrial robot. That's what they're for. They're super effective, super fast, and you're not going to touch anything, so you don't care about these dynamics. If you want to open a door, I mean, generally, the door will win. Like, the door has a set of kinematics, it follows the hinges, and if you try to do something that the door doesn't want to do, you will lose. Then it's not good to be stiff. Then you want to be adaptable, right? You want to flow with the door and just go wherever the door kind of leads you. And that's how we design our systems, because they're designed for these diverse environments where you're interacting all the time and you would like to adapt to the environment, not try to force the environment to be how you would like it to be. But it is different applications. So, I mean, I think industrial robots will still be there at scale 20 years from now, and probably way more of them, because they're going to get more intelligent.
Yeah, absolutely. That there's general purpose and there's specific, and industrial robots are very specific and they're very good at what they're doing. And it's going to be very hard for generalists to come in and be able to do it, because they're just, high speed, high payload, accuracy, everything else. The irony is probably going to be these industrial bots are still going to cost more than human. I mean, right now, the expectations, the humanoid is way more complex. Everything else is going to cost way more than industrial robot. But because industrial robot seems kind of simple, but they're still pretty expensive. And it's also the engineering goes around and becomes everything expensive. But in the end, because you can produce so much product with such high quality, it makes sense. And you're going to have that interaction between the humanoid and the industrial bot to be able to do what's needed to service that thing. Maybe it's feeding material, taking care of something on there because you have some sort of consumable that's out, or simple kind of maintenance task that is designed around a humanoid doing it. But yeah, the actual production, that's still going to be done by industrial robots. So the industrial robots don't have to worry about losing their jobs. That they will be safe. And you are right. They are going to get a lot smarter because they're too darn hard to program right now. And I would love to go up to industrial robot and just say, spot weld that car body over there, and then have it figure everything out and say, what are the spot welds you want? And then say, I'll go check the plans and the drawings. I'll look at it and have it figure out, like, these are the spots you want me to do, and just go ahead and do it, rather than actually having to show it. So industrial bots will get a lot of the same advantages that are being learned right now from the humanoid space, without a doubt. Like the one question I like asking, and maybe it's a bit premature, is like, if there was like one joint that you absolutely had to remove, which joint would it? And then the opposite one is, if you could get one joint absolutely for free, where would you add it? And then first, to be able to do that, we have to understand sort of what joints you have, how many degrees of freedom you have in the neck and the torso and everything else, and you can describe that.
Sure. So let me just quickly describe it. So there's a 3 degree of freedom neck. This is incredibly important for human-machine interaction. It's also incredibly important for the embodiment of the droid as an operator. And we're really working hard on making this as good an experience as possible, because I think in itself there is a market when you have this at home. for just embodying your own droid or other people's droids to be able to be somewhere else and do something. And this is actually one of the main things that I really enjoy about the one I have at home. Like if I want to cabin, I can just put on my headset and I can feed the cat, or I can like receive a package at the door, or like whatever, right? So I can have like a physical embodiment somewhere else. It's like get that experience incredibly good. That's so important to us. The arms, 2 arms, 7 degrees of freedom. I think that's pretty much the standard. It's what humans have. We kind of have the A tier with our scapula, and I'll give you the obvious answer everyone will say, which is if I got a droid for free, I would do the scapula because it's incredibly useful for manipulation. What if I got like a genie in the bottle and I could change something, I wouldn't actually do that. I would actually do a singularity-free shoulder. That's a different thing. Like, and if I got to remove one, probably go home and cry. I don't have anyone that I would like easily give up. Maybe a spine joint. Maybe we could get away with it. Maybe, but it gets really hard to reach the ground. Right? You could, yeah. You could try to be like very straight backed, and then bend over and touch the ground. You need quite a bit of hip mobility to do that, and so much of what you're going to do is going to be picking up things from ground, right? You don't have to squat every time we pick up something from the ground. So, yeah. But that's probably the one that I would choose. But it would hurt. It would hurt. There's no free lunch here.
This is great. You're the second one to say the scapula. I think it was Suzanne Gildert of Sanctuary that said that as well. And she said that at one point they had like 5 degrees of freedom in the neck, which was amazing because technically, like we do have a little bit more in the neck, but there's this big argument again, 2 or 3. And what I've said in like Norway, you have a pretty good football team up there, right? Which means Neo will be able to play soccer because he can do a proper header because he's got that extra degree of freedom, right? Whereas the other bots, they tend to not be able to do that. They can go forward like this and they can rotate like that. So again, if you're really thinking about it to do everything that the human does, sometimes it's almost the one I would take away if I had to take one away. And if I had to add one, it's the one I would add. So that's kind of why, along with the scapula.
Yeah, you just need to stand. You just need to come over here to Norway and visit and stand in front of the droid once and just look at it while it's like tilts its head and looks at you and you'll just be like baffled. And you're like, okay, we can't pull that one out. It's magical, right? It creates so much connection.
Yeah. Yeah. Now and the singular free shoulder. Oh man, you're right, because I look at the shoulder designs and I hate all of them. It's like, oh no, it's a roll pitch yaw. It just looks like an industrial robot wrist. Why are they doing it? We've got a ball joint there. Can't you actuate that? So I want to see someone solve that problem. And again, you just kind of get rid of that singularity there by doing it and then throwing it. So, oh man, you need help with the design. I'll sit there and work with you on it for sure, because it's a problem that needs to be solved.
Awesome. Okay. Thank you so much, Bernt. I don't know if you have any final words to be closing. If you have final words, if no, that I will close here. So, any final words you want to say?
Thank you for the great questions, and it's really fun to be on the pod and talk to all of you. And I hope everyone enjoys this. And let's do it again once Neo's out there, and we can give a lot of updates on how it went.
Yeah, we could just get a whiteboard, just start going up there and like sketching all kinds of things and talking about these. Because, yeah, it's wonderful to be able to talk to people who've had that experience, that have gone in there, that understand that. It's such a fundamental level, and that power density is something else. And definitely, yeah, 1X is a company to watch and to watch closely.